how many attendees are in the waiting
Just well, maybe I'll go ahead while you're doing that, if that's okay. Yeah, so I'm Jim Thorson. I'm at the Alaska Social Science Center. I was a student of Andre's 10 years ago or something. Used to be around here more. Here you go.
I'm Terrence. I'm in Andre undergrad.
And what are you working on?
Fluid dynamics and
Cool.
Hi, I'm Emily. I'm one of Andre's master's students, and I'm working on fish recruitment. I'm John, Trevor's master's students working on it, and see for
I'm Alberto Bedini. I'm a postdoc at Andre. I work on ecosystem models for development.
I'm a second year master's student of Andre's. I'm working on model diagnostics for stock synthesis models.
I'm Sabrina. I'm a postdoc with Andre and Tim Essington, and I'm working on broadly rockfish reproductive productivity.
Good job.
Yeah.
So I'm Mathieu. I'm postdoc with Jason Andre, working on the varying sea and the changing sea with the evolution of ecosystems and change.
Cool. Yeah. So, and then are the attendees in now? I don't see them listed on the attendee. Like, I'm curious who.
in the staff tab, the attendees.
Okay,
That's
got it. Okay, so is there a different staff tab? Is there a different tab here that I can click? Oh, audience view? No.
No, but if you go to the attendees, another way to look at this.
It doesn't probably matter, but
Maybe we expand it.
well, anyway, I'm kind of curious. Are you able to read the names to me?
Yeah.
Nico?
So Sabrina, Angelica Miller, Lisa Hillier, Hua Lee, Ian Stewart, James Iannelli, Jason Cope, Megan Burton, Michael Celestino, Michael Malinchuk, Nicholas Fish, Alina English, Ray Hilborn. That's it.
Okay. Well, yeah, thank you for doing that. So, kind of FYI stuff up front, you know, am I stealing your, did you want to say anything up front before I jump in? I'm scheduled to teach spatial temporal modeling for ecologists, a grad level course in spring 2024, and have a textbook that should be available for order before that with a GitHub repo on the kind of spatial stats thread. And then today I'm here to talk about phylogenetic comparative methods, which is sort of a 10-year thread I've been working on with colleagues. So basically the spiel is that, you know, PCM, phylogenetic comparative methods, or PCM, is, you know, has thousands to 10,000s of papers in EEB departments like evolution and applied and theoretical terrestrial ecology departments. You know, a lot of it was launched by Felsenstein here at UW, and I'd love to connect with them at some point. But somehow the PCM literature just never really connected with fisheries that much. And so, you know, I sort of reinvented the wheel a bit on kind of phylogenetic factor models, and have finally sort of realized that I can piggyback on PCM software. So this is sort of the first kind of workshop rollout of PCM software. And let's see, it looks like some of you guys have laptops and some don't. I'm not sure. Do people who are here want, I mean, I wonder if it makes sense to ask people to bring laptops. Like, I could just take 2 minutes and people can get laptops. Or okay, that was sort of my intent, was that people could, and I assume people have R installed and we can do the rest as we go. Okay, so let's just take take a minute to grab laptops if they're willing. Sorry about that.
No. It's running out of the house.
I get it. Yeah, so, well, I mean, everybody's close here, so I'll just kind of keep going. And then people online, I mean, it's more fun for me to look at people on site, and I'm just hoping people online can interrupt me if they have questions. So can I just do a demo? Like, somebody interrupt me online.
So there, Nico has to unmute.
Oh, do you want to, could you unmute everybody, Nico?
Yeah, you should be able to unmute every.
Hi, Jim. This is Ian. I'm interrupting you.
Yeah.
Ian Taylor.
Yeah, I'm unmuted now. This is Ray.
Access, they don't mute themselves then.
Okay. So hopefully everybody online heard all that. I suddenly was muted, or maybe I was muted that whole time. Can people online, can somebody just jump in and say something and we can test the speakers here?
Testing, testing. Can you hear me?
Talking.
I heard it, whoever it was, but it doesn't sound like Tim did.
Gonna work on that a little bit to see if there's a way to get.
Yeah, it should be good for you on computer. But they're speaking, it's fine. It's just not.
Well, okay, so maybe people off site can. Can you hear me better online now? I'm trying to see how this will work with the off.
Yes, you're probably on your headphones. You should probably undo it.
Yeah, perfect. Okay, sorry about that, Ianelli. Okay, so I can hear Ianelli. I'm gonna take off the headphones and see if you can actually talk loud enough for other people to hear you too. Yeah, that's a bad idea. I'll just repeat your questions. So anybody off site, just jump in at any time, because there's maybe about 10 people in person and 15 people off site. And so between all of us, I think we can accommodate any questions as we go. Okay, so yeah, so Phylosem is an R package that's up on CRAN. We're up at 1.1.0. The latest major, minor release up to 1.1.0 was putting out this vignette PCM and fisheries, which redoes the Honig method for natural mortality using PCM, and that's associated with a paper in press at Fish and Fisheries. There's of course a GitHub with this as well, where people can do issue tracks and tracking, and co-authored by me and Wouter van der Bijl, who is a brilliant postdoc at UBC in the EEB department, and also author of Philopath, which is sort of a related method that this method in some sense generalizes.
Hey, Jim.
And then, yeah.
Are you sharing a screen?
Oh yeah, thank you. Okay, thank you. Too many buttons. Okay, so I just shared a screen, I think. Can you see my screen now?
Yeah, we can see it. We can see it.
Great. Okay, sorry about that. Yeah, please keep jumping in. Jim Ianelli helpfully pointed out that I wasn't sharing my screen. So, yeah, and then Phylosem, the R package is documented in this this paper that just came out in the Journal of Evolutionary Biology yesterday, and so that's what I'll be kind of focused on today. So the big picture point here is that PCM, let's say there's 1,000 papers that have been published in terrestrial ecology, and let's say there's maybe been 10 in fisheries. Anybody jump in? Sabrina, I think you've looked into it. I don't know if you've published on PCM in fisheries. Okay, I know that I don't mean. Yeah, great. Okay, yeah, and I don't mean to, by saying that there hasn't been much work, I don't mean to ignore the people who have done some work in PCM and fisheries. So anybody feel free to jump in if you want to kind of highlight cases that you're aware of. Yeah, so basically my claim is that, a lot of fishery science is founded on comparative methods for biological reference points, for parameterizing ecosystem models. And there's a huge amount of work to do in terms of basically modernizing all of those sort of foundational studies to use phylogenetic comparative methods. And I've been trying to do that in this project called Fish Life over the years. So like Fish Life, we just published the latest iteration of last year in Methods in Ecology and Evolution with this team of authors, Aurore Moreau, who's in Malin Pinsky's lab, Romain Frelois, Bastien Marigot is in France, Sarah Friedman is here at Alaska Center and is giving one of the seminars coming up on diversification rates. Deng Palomares, runs Sea Life Base, Malin Pinsky recently in California, and Sam Price and Peter Wainwright are both big kind of fish Evo people. So we did this. Yeah.
Taylor, could you go to display settings there and change it to mirror the displays? Because right now we're seeing
it in presentation.
The presenter view.
Great, thank you. So do I do swap presenter view and slideshow?
No, duplicate
slideshow? Okay,
yeah,
perfect. Thank you.
Thank you.
Okay, yeah, Ian Taylor pointed out that screen wasn't being shared very well. So I'm sure I'll keep having technical things, and so people really do need to just jump in because I'm kind of intending to toggle between different software here. Yeah, so not to spend a lot of time on this, but this is sort of an example of Fish Life, which is the most recent version of this like 10-year project I've been doing, where, previously we merged FishBase and the Ram-Meyer stock recruit database to get things like generation time and intrinsic growth rate for all fishes. And this most recent one was sort of merging in the Price Wainwright morphometrics and a bunch of behavioral and ecosystem ecology traits. So like you can classify traits as life history traits, like those are demographic parameters we use in stock assessment, but there's also morphology like gill rakers or meuristics, like a lot of classic, stock structure stuff before we had modern genetics. There's behavioral traits, which are things that like an ecosystem modeler might care about for driving species interactions. Diet traits, like, trophic level, like if you're Trevor and you want to re-update your fishing through versus fishing down versus whatever, you need trophic level. And so, diet and trophic level traits, metabolic rate, there's a big push at Alaska Center to refound everything on bioenergetics. And so, Wisconsin model or otherwise, there's a bunch of bioenergetic parameters. These are all basically everything we know about fish ecology can be thought of as a trait, a species trait or an individual trait, and we're trying to figure out, kind of a unifying framework for how all those connect with one another. And so we did this for fishes, and ended up with this big sort of phylogenetic structural equation model where we pre-specify sort of boxes and then hypothesize linkages between those traits. So this hypothesized trait network was sort of based on bioenergetics, like temperature is kind of the root of it. And then that goes to length L infinity, which then radiates out. So it's sort of this like Ken Anderson style size structured kind of theory of how fish traits might trade off. But the point is that, we publish this kind of third iteration of Fish Life and have good cross-validation performance, and we can plug in the traits, this archetype model, and get the Wine-Miller-Rose typology. There's kind of appealing things about this, I think. But at this point, Fish Life is like it's too much of a beast. It's like the software is specialized and probably nobody feels comfortable running it on their own. And, if I really think that PCM is something that has hundreds of projects to do, the key is figuring out how to refactor it and make it very simple and break it into like a consortium of some people that will work with me or without me, or I don't care, on the database assembly. There's the methods, which is the focus of this talk when I get to it. And then there's the repositing of output. And all of those are bundled into Fish Life as a proof of concept, but I need to kind of unbundle them And so basically the unbundling is, the first step of that is making Phylosem this sort of simple to use software that can do all of the fish life kind of stuff. So that's all I was going to say about fish life. Does anybody want to jump in on that thread? I've got kind of 3 little PowerPoints I was going to cruise through before getting into software. Okay, so the kind of core of this today is, and I'll switch the display settings again. Thank you for teaching me that. I never knew how to do that. Yeah, so there's this R package Phylosem. So kind of one way I pitch this is that, like, with, you know, fish life is a little bit like VAST. You know, kind of like a Swiss Army knife that at some point gets too big for people to like using it. And so I'm trying to, you know, Phylosem is basically like the SDM-TMB of fish life. It's like, you know, what SDM-TMB is to VAST, Phylosem is to fish life. It's sort of a simple, small code base that anybody can read all of the code if they're interested in PCM, and everything's documented well, and it has multiple vignettes, and it's on CRAN, it has minimal dependencies, and, you know, kind of generic S3 classes for doing analyses. So yeah, so that's the intent, this sort of minimal, kind of in the like Hadley Wickham sense, kind of single purpose R package. And if anybody's interested, Ian Ellie, I saw that you had like a little hex thing with a picture of a pollock that you put on your package. Like, I feel like people love, I don't know. Yeah, I'd love to like figure out how to kind of Wickhamify it, kind of make it look like sort of other single purpose software. And if somebody is interested, I'd love some help. So yeah, so PCM kind of broadly is sort of a way to connect kind of applied like fisheries management with evolutionary biology. That's one way to view it. And so, you know, essentially it used to, well, I'll get into this in a second, but the kind of modern structure is that we have evolutionary biology that define, you know, molecular traits like neutral markers, and, you know, with whole genome sequencing or whatever, you know, they can come up with information about evolutionary relatedness, and then they compress all of that information down into a tree, like a phylogeny or a dated chronogram, or there's different terms depending on differences in the tree. And then that tree is the output of the Evo folk. And then, you know, so that gets from the top left box to the middle right box. And then that tree is essentially a structure on a mixed effects in a big generalized linear mixed model. So, you know, in a generalized linear mixed model, you say what random effects are independent of, you know, in IID, or they have a random walk or whatever. PCM is basically a set of methods for constructing the covariance among a bunch of different random effects based on that evolutionary tree. And it's, yeah, totally. Totally, yeah. And so I don't do that top piece. I mean, I'd love to, yeah, I'd love to talk with somebody who does. They, you know, people make these dated trees. And so for instance, like Roboski, you know, in the stuff I'll use later, Roboski's lab has a package called Fish Tree that contains a dated chronogram, which is just a type of tree. And it, you know, it has every edge in that graph has a length, which is millions of years, you know, so you can, and we'll see that in a minute, but you could also have an undated chronogram, which is just sort of the same tree, but without branch lengths. And then taking a step back from that, you could just take, which is what I used to do. I used to take a taxonomy and convert that to a graph and just assume that different edge lengths, like species within genus has one edge length and genus within family. And so there's simple to use software to take a taxonomy and convert it to a tree, which is what fish life does. But Phylosem just assumes that you have a tree. So like, for instance, like in VAST, you put in lat long and it has software that converts that to a graph using the INLA stuff. And that's kind of merged into VAST. STM-TMB just assumes that you make your mesh and passes it to it. And so it's easier to use, just use a common data structure. And similarly, like I'm using the R package called APE, which is sort of the core. There's only one R package that does all the data structures for trees, and I just use that because that's what people use. So anybody doing comparative methods in fisheries, there's a couple R packages they should know. One of them is APE, and that just has a class called Philo that we'll use a lot. And there's a couple kind of core dependencies like that. Yeah, so another way of seeing this is how I got into this, which is like, I mean, my grandpa was a fisheries biologist, but I remember a Christmas where I was bored, kind of grumpy and bored at home, and saw this paper on Ecotome that kind of transcribes a bunch of traits of different elves and dwarves. They have outgroup cross of dwarves, and they're like, what, is the Keebler elf related to the Middle Earth elf or the house elf, like the age-old questions. And so they've got these behavioral characters and morphological characters, life history traits. Some of them are missing, so like the dark elves and the light elves, like there's no longevity information. So maybe you want to like fit a tree to these elves and then impute missing elf information. And doing this, they reconstructed this sort of phylogram of elves, where the outgroups like dwarves, fall out with, David the gnome and the fairy and the house elf are kind of the outgroup. And anyway, so I mean, there's just zillions of people. Like anybody who's gone through an evolution department has spent a lot of time thinking about this, and it's everywhere except in fisheries. So partly the prompt is just to like think about evolution and what it can do for us. Yeah, so the cartoon here is basically like you have inputs and you have outputs. You have an input, which is a phylogenetic tree. And so here I'm showing red is rockfish. I'm not going to remember the other colors, but if you have this ape, this philo object in class ape or package ape, you can prune it down to a given set of taxa. And then you can display it as this like radial tree, which is that top left, or you could do it through kind of a tree on the right. So you combine that tree with a data frame of traits, and it could be categorical traits or continuous traits, and like, Honig, again, like a lot of fishery science is just based on scatter plots of traits, and then they're built into biological reference points and hugely important for determining fisheries policy, even though most people don't ever personally do research on those trade-offs. Instead, they do, and then when people do it, like the Honig method or the poly method or these kind of classic things for thinking about trait trade-offs are just scatter plots where people did linear models through them. And, a linear model you can represent as a structural model where you say, in this case, log m might cause log L infinity. I forget why I did it this way for this example, but, with the parameter beta. So those three inputs you put into what's called a phylogenetic structural equation model, and it'll output imputed trait values. I kind of wanted, anyway, I wanted to do this for the elves, I swear. I just didn't get around to the coding of it. So it would be another fun thing to do. But, and then you run it and it'll estimate parameters and it'll impute missing values for these traits, which you can display in sort of canned software. Like this is outputted with a package called phylosignal package. Yeah, so the inputs, the ape ape is this kind of core in kind of dependency that has the philo structure, you know, which either you can convert a taxonomy to a phylogeny or you can just download somebody's phylogeny. SEM, I'm using this SEM package that Fox at McMaster developed to specify kind of boxes and arrows. And so in the bottom right, this model is a text, a character string that's saying, in this case, variable DD goes to variable RS and with a parameter called P1. BM goes to LS with a parameter P2, BM goes to NL with a parameter P3, and NL goes to DD with a parameter P4. And so that structurally makes this graph on the bottom left where BM is the root and it goes to NL and LS, and then NL goes to DD and DD goes to RS. So hopefully people can crosswalk that. And that's outputted. That there's a bunch of different packages that make the, you know, graphs from the output of this. So no, I'm sorry if I'm going, yeah. Totally. Yeah, so this is a data set that Wouter simulated for kind of a made up rhino lineage, and put up with his package. And so I wanted to show that I could replicate the results in PhyloPath, where this is the core example. So BM is body mass, and I literally don't. Yeah, exactly. So yeah, so I mean, the one I've obviously thought more about was the other one with this one, where, you know, this is just a fancier version of that same thing, where you know, one trait might be temperature, which in this, I mean, it'd be nice if I had a good temperature record for all fish. This isn't a good one, but I mean, it's just a measurement of temperature in fish space for every fish in degrees Celsius. You know, if you want to be fancy, maybe you convert that to the Arrhenius coefficient, like it's like 1 over Kelvin. You know, who cares? You know, and then log length infinity is just in millimeters or centimeters, and so what this is saying is, as temperature goes up, L infinity goes down. So for every degree Celsius it gets warmer, you expect L infinity to go down 2%. For every percent log L infinity goes down, goes up, you expect growth, the von Bertalanffy K, which is that log growth rate, to go down. Yeah, exactly. If it goes, you know, like if it goes up, if log L infinity goes up 10%, then log growth rate goes down negative 6.5%. And the point of this is you can get these indirect effects and direct effects. So temperature has a negative effect on length infinity, and that has a negative effect on log growth rate. So temperature has an effect on growth rate that's positive via length infinity, and it also has a separate positive effect directly on growth rate. So this goes back to like Sewell Wright, who is also like the founder of landscape genetics. Like if you know the term fitness landscape, that was like Sewell Wright's term. He also made something called path analysis, and this is just sort of back in the 1920s. This is sort of a path diagram. Sewell Wright, as far as I understand it, got in a fight with Ronald Fisher, who is also a statistician and geneticist and a white supremacist, Nazi party member and bully. Yeah, and brilliant. I mean, I use a lot of stuff from both of them, but you know, Fisher basically like set back the world of causal statistics by just like personal animus. Yeah. Yeah.
Like there's a whole history behind it, even though it would be like it's largely applicable to ecology and looking at, you know, stepwise causal relationships. So that's like the big thing. So you're drawing links from, you're saying this is going to cause this and this is going to cause this. And yeah, it was just, he was like bullied out of the method, like he was like just put down, like, no, that guy's not doing anything good.
Yeah. Yeah, and And I'm so sorry. Are you willing to unmute just so people online can hear you too? Or you have? Sabrina was just reiterating that science is driven by personalities, and like, yeah, I mean, like, what was it? Somebody said like the mark of a like a famous scientist is somebody who can like set back the field 30 years. Like we're all bricklayers, and like science will get there regardless. And like if you're a good scientist, you help push the field forward, a little bit, but and like causal statistics is, like Judea Pearl has like brought back the Sewall-Wright path stuff, like the field, and machine learning has jumped off Pearl. So like Sewall-Wright got there, but like Ronald Fisher, like because he wanted everybody to do agricultural experiments and ANOVAs, like managed to push out causal statistics for a long time.
Are these SEMs hypothesis for how these stuff are linked together, or is it like we have a pretty strong evidence that I'm curious if we can set them up differently.
Yeah. So and it's Emily Salinger. So Emily Salinger was asking about like how we set these up and how much we can. Are they like hypothesis testing, or how much can we learn about the structure of it from fitting these models? Maybe is. So one thing I'd love to do with this kind of fish life thing is sort of work with experimental ecologists. So there are long-term evolutionary experiments on guppies, for instance, multi-generation experiments where people do selection regimes on M, and then look at how other traits change with it, if you exogenously change M. And so that would give direct information about the M to age at maturity, length at maturity. And I'm assuming this model implicitly is saying if you change M, you expect nothing to change in log L infinity, which is almost certainly wrong. So, the best way to get information about causality is experiments. And you can feed like for instance, like you can't learn an arrow connecting log L infinity to log natural mortality and estimate the other arrow at the same time just with observational data. But if we have an experiment measuring one of those arrows, we could hardwire that in and then estimate the other arrow from data. And so, basically like this, there's sort of this like, fishery scientists have not, historically used a lot of experimental information, to think about, like the biggest place it comes in, I would think, is the fishing induced, rapid evolution stuff, the Conover and Munch and so forth. And there's a lot of arguments about the applicability of it. But, SEM would be one framework for bringing in experimental information and looking at how it affects biological reference points. And I hope it would move that forward, that kind of endless discussion forward. I'm sorry, that was a big rambly thing. Did that? Yeah. Yeah, so one thing we could do, and remind me of your name again? Terrence. Yeah, so Terrence was asking about cyclic pathways. So you could have maybe I'll just switch over to software for a second. Let's see. So I'm trying to think if either of my good examples are gonna have cycles. One of the examples, and Miko, maybe you could share that URL again. So one of the examples here is Q over B. So ecopath models are a mass balance model that comes along. As far as I understand it, like it's partly developed at the Alaska Center by people like Lavatsu in the 70s, and then there's a lineage of people doing mass balance models. UBC comes along and makes the most famous software for it, but it's not like UBC invented it exactly. And I think that Willy Christensen would agree that he's deeply indebted to people before him in developing the method of ecopath. Anywho, so ecopath, one of the core parameters in the way ecopath with ecosim is built
is this consumption over biomass, or Q over B trait that says how much a fish is expected to eat per biomass. And so Q over B is is like 50 for a seabird because they're warm-blooded and burn energy flying around and doing crazy shit. And it's like very low for arrowtooth flounder, say, that just sits on the bottom and has disgusting meat, and and it probably intermediate for halibut, or for forage fish. So there's some kind of evolutionary trade-off of Q over B with other stuff like trophic level or feeding mode or maximum size or growth rate. But I would be willing to bet that most people in fishery science, even in doing ecosystem models, have not actually played around with sort of Q over B life history trade-offs, because it's just not, even though we're empiricists, like everybody does kind of hands-on stuff with a stock recruit curve, but it's just not our culture to like do inner training, a lot of empirical play around with it kind of stuff with ecosystem parameters, as life history trade-offs, as far as I'm aware. So one example in this URL that Miko hopefully distributed is this Palomares and Poly 1998. So it's just a digitized version of a data set. And here, maybe I'll pull up the paper just out of, I'll say that, I'm like hugely indebted to both Deng and Daniel Polly, and Daniel is brilliant and can be extremely friendly, and we should all be lucky to get to chat with him. One of his many papers that's super interesting is this one. They define food conversion efficiency as Z over Q over B, so mortality divided by that is essentially like how much energy is wasted in a trophic level, for instance. So if you want to think about, and I think we all probably do, like what's actually happening in a food web, it's not a bad place to start with thinking about, ecopath, and then trying to think through like what, how asymptotic weight affects, like why is it forage fish burn much more energy per gram that they put on compared with, a rockfish, say. So this paper has, put the data in it, which I just grabbed and shared with you. And here I'm going to load Phylobase. Probably won't. Well, I forget. One of these packages, I think it's PhyloSignal, just got booted off CRAN. But you can they'll get it back on CRAN. It's just normal CRAN stuff. Ape is the kind. Actually, I think the way it's set up, I could do this in a simpler way, where some of this is loaded by Phylosem automatically. But are people online able to see my screen okay? And
yes.
Great.
Yep.
So this is the kind of database that we got from Palomares and Poly, where you've got, species, locality, T is temperature in Celsius, total length. I don't remember what some of these are. Somebody would have to look in the paper. I think I put it in the notes down below. I think K and M are growth rate and mortality rate. S, H, D, and P are indicators for a different habitat type, I think. Let's see. So hopefully I took good notes later. Here I convert the species. Oh yeah, I cut out sort of some extra. One of the biggest issues is that we in fisheries don't actually call the same species the same thing, and we have very strange use of like subspecies in our, so like one piece of advice for people who are interested in this is everybody just start using the worms ID. So worms is founded by Deng's husband, who is part-time between Fishbase and part-time between the Museum of Paris, and I forget his name. but he's the husband of Deng Palomares. And he founded Worms, which is sort of like an attempt to clean up all of the taxonomy of fish. And they've pushed it much further than anybody else. And so anytime we have a database where you publish stuff, you should just put the Worms ID in it so that other people know, like if Thorogra calcogramma, which used to be pollock, switches to Gaddis calcogrammus, you don't have grad students being like, what the fuck is Thorogra calcogramma later. Just use modern methods and refer to an ID like you would, would normally. So yeah, and then here I'm just making a column that's I just use genera species with an underscore because that's the way that Roboski published his stuff. This is a bunch of stuff in a tax size package to get the Worms ID, which I kind of briefly started messing with and then just kind of abandoned because I don't really care enough in this example. But so the fish life package, which I loaded, has this fish tree complete phylogeny, which is like a modeled phylogeny. So it'll take a second because in loading the package, it has to load this consensus tree for 28,000 described fishes. I'll say like fishes, I mean, talking with Deng and her husband, like there's like another described fish every day and has been for like years. Like it's the most diverse set of vertebrates and it's a big taxonomic nightmare. And so we're again kind of lucky to work with people like Roboski for the fish tree, or there's a Stein database of phylogeny for chondrichthyans. So like, people at Simon Fraser are kind of working on like a big shark replacement for Fishbase called Sharkopedia, I think. So anyway, so I've got ape loaded, so I can use functions like ntip. So tree, which is this Roboski modeled phylogeny, it's a rooted tree. I could plot it. Let's see, I'm just gonna cut to the chase because I hate plotting it because it's so big. I'm gonna try to turn off labels. So plot phyllo, I don't know if this will make it less annoying. Show tip label, so I'll just try to turn that to false. Plot tree, let's see if this, it'll just take a while because it's, so a phylogeny is what's called a bipartite graph, where in theory, the probability of two splits happening at the exact same moment is 0. And so every split in the graph is one thing becoming two things, and that's sort of the classic view of, that's like the modern synthesis, of evolution. And so if you have 3,156 tips, which is species that are described in this dated chronogram that's shown on the right-hand side, you'll have that many minus 1 ancestral edges to describe this tree. So, and edge, I forget I don't walk around with the syntax in my head exactly, but yeah, so the math almost, well, anyway. So the total number of edges in this graph is 63,000. And, essentially it's just a spatial model on a fixed domain. We have a census of all fish, essentially. And so if you want to predict traits for a fish, you just replace your graph in a spatial model with a tree, and then you just do all of your kind of stats that a person could learn for spatial. I mean, that's how I got into this, obviously. Yeah. So, and then I try to crosswalk these two databases without really spending a lot of time fixing obvious errors. So the stuff that is in both databases is these 55 species, and I subset the data down to those species, and I get, I don't know, maybe 80% match. I'm sure somebody could look back and look at what got dropped there and do better. And then I can just subset the tree using this keep kip function. So the tree, you know, now that I have a few species, I can plot the tree with the labels, and it won't cause my R session to freak out. So on the right-hand side is this sort of dated chronogram of fishes that are matched up with that Q over B analysis of Polymeris and Poly, where tilapia, we've all taken fish. I assume people have taken fish biology. I mean, these are some forage fish, which are all related. There's some salmon, I guess, in here. I don't know. Here's a Sebastes, that's fun. You know, but I don't really know these. I guess Sebastes is right next to Epinephalus, which I think is groupers. Lamonda, which I think is one of the flatfish I should know something about. So anyway, I mean, you can kind of start seeing the coverage and linking it up with species you might know something about. Okay, I think there's a flashing question. I don't know if somebody, maybe that was you, Miko, posting the URL again. Okay, so and then I'm just selfishly just kind of rescaling. It'll make it easier for me to interpret parameters. So this is the depth of the tree in millions of years. So each tip, I guess the furthest ancestor is 177 million years ago. So I'm just gonna take, there's a slot of that. I mean, if you look at the tree object, which is my name for the copy of that philo, well, I'll just show you. So tree is in this philo class, which is the kind of class for PCM in R, in that package ape. And it has a slot that's edge length. And so I'm just rescaling it to 1. So let's see. I'm not going to remember how to do this well offhand. Yeah, so that's not labeled right. There's a way I could put an axis label on this in ape, but that wasn't it. Anyway, so did I do that? Let's see. Yeah, so now I've rescaled it. I'm gonna scale the traits the way that they did in the paper. So traits is now, and I labeled it here. So Q over B. So that the relationship that they did was consumption has a relationship to, it has an intercept, weight infinity effect. T prime is the Arrhenius term. A is aspect ratio. So they think that if you have, aspect ratio is the height of the caudal fin squared divided by the surface area. So it's high for a tuna and it's low for a guppy. And the idea is that highly active fishes have a different shape of their caudal fin, kind of based on evolution and kind of water mechanics. And so that would be a good thing in this relationship. H is an indicator for herbivory or detritivores. And so, you know, you put that in to this database of traits. And here I'm, you know, again, I'm rescaling degrees Celsius plus converting to Kelvin and dividing that, you know, taking the reciprocal of that, and that's that Arrhenius coefficient. Let's see, I forget why I did this next function. Oh yeah, that's just figuring out if I have different values within a species. So I do for everything except A for some reason. So that'll affect how I set up the model. So the way that you can run this, hopefully this works, is you know, it's basically just using an SEM to replicate a linear model. So I'm saying, I'm doing the kind of boneheaded model, which is just saying everything is exogenous and all independent variables just have a direct effect on the dependent variable. So that's, you know, basically a linear model is a nested submodel in an SEM, and linear models almost never actually match the assumptions we assume about exogeneity. But you can, you know, an SEM makes it explicit what your assumptions are. So, and then here I'm, this is the syntax for phylosem, where I'm kind of skipping around in workshop style. But you have to specify what the family is for each trait. So I've got 6 traits, and I'm going to assume that there's normally distributed error on 5 of the 6, and then I'm going to treat one of them as if it's fixed without error. And that decision was because of the data I have. So I've got, within a given species, I've got some positive standard deviation in the values of Q over B. And that's because they've got these replicated measurements for stock within species. So like, for instance, Oreochromis niloticus has a bunch of different rows corresponding to different studies, but they all have the same value of A, whatever that is. I guess that's aspect ratio. So they clearly merged a single database, a single measurement of aspect ratio, like from museum records, with a bunch of localized ecological measurements of the other variables. And so given that design, I can't estimate measurement variance for A. I just have to assume that's known perfectly. But the other ones, there is measurement variance that I'll estimate the magnitude of. And then I'll talk about the estimate lambda in a second. First, I want to see if this runs. So it runs in 1/10 of a second. It's got a summary function, it's got a AIC function, etc. And then this, and then you can do these sort of basic, the minimal implementation is to just have a bunch of coerce functions that coerce it to other data objects. So I don't have to, unlike FAST, I don't want to ever get into making plot functions again. And so, I'll just have coerce statements and let people use other packages. So in this case, I can convert it to a fitted DAG, which is this object class from Philopath, and I can get their plot, I don't love it. It doesn't have an arrow for T prime because that's the largest magnitude and it's just too big for it to have plotted. So you get to complain about other people's plotting software instead of your own. But, it has a coef plot. So here's like the coefficient plot with standard errors. So, as you get larger body size, you get a lower consumption over biomass. That makes sense to me intuitively, as metabolism scales less than proportionally with body size. So they're spending less energy on metabolism if it's a larger fish. As you get a higher temperature, you get lower Arrhenius, and a lower Arrhenius causes a higher consumption of biomass. So this overall is saying you have warmer temperatures, it causes higher consumption over biomass, which also makes sense to me. If you have a high aspect ratio, you get more consumption over biomass. That's the sort of hypothesized sort of biomechanics link. And then if you're an herbivore or a detritivore, an herbivore has the highest consumption over biomass, I guess because their prey is lowest energy density or something. And detritivores have also elevated consumption over biomass. Yeah, so I've been talking for about an hour and I need to move my car at some point. I don't know if anybody, I'd be kind of happy to take votes on what to do kind of going forward. We could switch, I could either like set people, we could just see if people can kind of get this running on their own for the other example, which is the Johnny Armstrong gut capacity to body size nature paper, or we could just play around as a group with this one, or we could go through more PowerPoint slides. What? I think any opinion. Yeah.
While we're deciding, I have a question about the model structure in that slide where you had temperature as the first splitting point.
Yeah, in the one that I did for Fish Life back kind of a while ago, or the Polymeras one.
This one here.
Yeah.
How robust would this structure be to variability in the input data? Could it be something like a regression tree where you have a variety of very different structures that could explain the data almost as well as one another?
Yeah. So, and I'm so sorry, I don't recognize your voice. Can
Oh,
you?
sorry, it's Mike Melnichuk.
Okay. Yeah, Mike. I'm sorry. Yeah, great.
No.
Yeah. So Mike is asking basically about like, like a regression tree. There's this there's this book I love called The Elements of Statistical Learning by Hasty Tiptrani and Friedman that basically makes the point that if you have a bunch of uncorrelated learners, you have weak learners, and you average them, you get a strong learner as long as they're uncorrelated, and that's the basis of a regression tree. So like, you might have a bunch of different learners with different structure that all fit the data equally well, and what do you do with that, and what inference do you draw? And yeah, Mike, I mean, the honest answer is like, I have no fucking clue, and I haven't played around with this that much. And, PCM, the PhyloSem is public software, and I'd love to think with people about kind of multi-model inference. So
are these coefficients and are the input data all based on the species level values from FishBase and SeaLifeBase?
So yeah, Mike's following up and asking, is it all based on species level, or can you do like stock within species, I assume? So Felsenstein, like the original theory is like so first of all, a tree is an evolutionary object, but it's also an animal model. Like if you do crossbreeding experiments, like L1, first, second generation experiments, that's a tree as well. And in fact, Pagel's lambda, which I ran in this other one, is identical to the animal model. Like if you want to estimate a selection coefficient, like in quantitative genetics, that is identical to the Pagel's lambda that you could estimate with this software. So if you have a selection experiment, you could just plug it into this and run an animal model, and it'll work, and you'll get useful. I mean, it's useful for that. The vocabulary in PCM is that there's like a within and between species level, basically, and like Fish Life. Well, anyway, the easiest way to do it in the software here is basically you could take the Roboski tree, and then you could use this add tips function in Ape to basically add a tip for stock within species, and then estimate Pagel's lambda, and that would give, instead of like a measurement error variance, or like a variance at the tips are the stocks, and so you could get the proportion of variance for the stock within species separate from the evolutionary variance that you're also estimating. So there's sort of this, I don't know if that made any sense, but like there's sort of these software tricks that, and I'm just trying to keep PhyloSem on kind of mainline PCM software interface. So, the kind of world is our oyster for coming up with ways of representing that within species, among stock within species, or among individual within stock within species, and there's ways to do it. Yeah, any other instincts about like what's an efficient use of our time as a group? Hey, Jim Bob, you want to jump in?
I'm kind of at odds. Sorry, I don't have any brilliant plans.
Okay. Yeah, I think Jim didn't have a strong suggestion. Well, yeah, maybe that would be. So I'm embarrassed that I need to move my cart. There's like a 2-hour parking limit, and I showed up early, and it is what it is.
Maybe just on a very practical side, you could do like what you did for Pacific Cod, like soup to nuts.
Yeah, totally. Okay, so Ian Ellie was suggesting, so basically like I'll get people set up on a task here. So, and then I'll move my car. So, this fish and fisheries paper is like a goatee, fish submission. And, it's like basically like the finger wag, sort of like, let's use PCM and fisheries, but it has sort of a specific example. Well, first of all, you can take a taxonomy and convert it to a tree. So if you do that, with a Roboski phylogeny of 6 species in the top versus converting kingdom, phylum, class, the taxonomy to a tree and computing the correlation, you can see that the correlation on the bottom, which is from taxonomy, is pretty similar to the correlation from a phylogeny. But of course, like the phylogeny captures correlations between Merluccius. Oh man, I'm sorry. I fixed this later. This is the right-hand plot doesn't match the tree. So there's a bug here that I fixed before the paper, but didn't fix in the slide. But the point is that there's a correlation in the tree between Lujanus and Merluccius that makes them more similar than in Growlus, which should show up in that correlation if I'd done the labeling right. So that was one point. So if you do the Honig method again, and I've got a vignette that I'll get you set up on, the Honig method, it tries to predict mortality rate from longevity. And if you do that with a linear model or with PSEM, phylogenetic structural equation models, you get about 83% of the variance explained if you do a jackknife experiment using the Then et al. Database. So you don't really gain anything using phylogenetic structural, phylogenetic inference in longevity. But if you try to predict M from L infinity and K using a linear model, you only explain about 40% of the variance. And you can get that up to, and again, these numbers are not updated since I submitted the paper. I mean, this slide's slightly out of date, so the numbers are slightly wrong. But you go from approximately 39% of the variance to about 53% of the variance if you use phylogenetic models to do, model the covariance among species and condition on that covariance when predicting. And the reason is that essentially the intercept, this is essentially a big random intercept model that PCM is doing, random intercept GLIM. And the intercepts for the relationship between M and longevity and growth parameters, the way I'm setting this up, the intercepts for rockfishes in red are typically high. They typically have a higher longevity for a given growth parameter than fishes on average. And that makes sense. If you think about rockfish, they're obviously living in rocks and they have spines. And the whole point of a sebastes is that you don't want to eat them because they're cryptic and they stick in the rocks and they're pokey. And, and they mature late in life because they know that they're not going to die as fast as other fish. So, it'd be fun to figure out, bring in spines and body armoring to look at these relationships, and that's an obvious next step. But if you don't have kind of obvious morphological traits that predict M, then you can still do the next best thing, which is condition on related species and predict that all else equal, a rockfish will have a higher longevity for its growth parameters than other fish. So that's the heart of this paper. So it's in if you go to GitHub and, clone or download a zip file, tell me if anybody wants that slower. I've got a fisheries.rmd script in here. And so the first step here would just be trying to run this R markdown vignette locally. So I guess that's my assignment. for 10 minutes while hopefully I find a quick parking spot here. And Leaky, I think I have your phone number to call you if I'm like really struggling, and I'll just, okay, cool. Does anybody have any questions to get started? I mean, so again, like to be more specific, I think it'd be helpful if people want to run this script and they could just start playing around with either the SEM structure that I specified here, or they could start playing around with different specification of the estimate OU, estimate lambda, estimate kappa transformations, which are documented in the reference docs. So like Booleans indicating different transformations of the phylogeny. Does that sound like enough direction? Okay. Okay. I'll be right back.
There's a lot. Like I am still. So what we're trying to do with rockfishes, and he has a lot on his website about comparing different methods. So comparing like hierarchical models and like how does that compare. So like with rockfishes, like work we did a long time ago with JJ, thinks that the length fecundity relationship that we use in the assessments now is like there's a phylogenetic signal based off of just like these linear models, like hierarchical linear models that we came up with showing put in like the subgenre, there's like a signal there. So, like species more closely related, have stronger returns. So that's like what we're trying to do is like put in some of that into one of these and do like a paper's already been done. It's already shown there's a phylogenetic signal. So what if we use this method? And then I guess kind of the benefit is so now what I'm struggling with is like I think what you asked setting up the SEM because there's different ways to do it and different assumptions are drawing possible lengths. And like so where there's some other parameters like oh well fecundity might be also by large size, a lot of variation in all size of the species. So put everything 1% all larvae from it. In fact, so you can put it, you can kind of look at different place or habitats. So I think you could get at convergent evolution through that, which I think would be kind of cool. That's one question with the rockfishes. Some of them have a different reproduction strategy where they reproduce multiple times a year. Some of them are like limited to one. To me, it's not the most closely related species to do that. Species in Southern California do it where they have different. So that to me, that's like want to have some kind of like understanding of those causal relationships that you're developing the model. Because yeah, maybe through AIC you just get a better fit, but it really, yeah, you have to be a little bit more. Yeah. That also, there's just a lot of things you can do with them. Like you can look at pools. So you don't have like an exact measurement, but there's things that like feed into that. Like for rockfish, what I tried. But I was trying to say like there's something in the environment that affects the body composition of the fish that can be the fish. But what is the environmental variable? But you can kind of come up with a latent variable saying, okay, there's something in the environment. This is what I know about the environment. You can kind of do that and have like latent. I feel that, but yeah, it's a lot. He sets it up very simply, and then but it's kind of cool. And that's pretty cool just to visually see that.
I think it worked. I like now that there's not like paper things, I don't really know. I don't know. Yeah, I don't get it. Yeah, so did anybody try running through the vignette? Yeah. Oh no, your laptop crashed or while running Philostat? I mean, did it did. Yeah. Yeah, I mean, the goal is to like have the software be more stable than the rest of the unstable house of cards we all work on. Yeah, so did anybody online want to share any? Did anybody manage to install the package or try running the vignette?
The one that is off brand at the moment is Philostat.
Yeah. 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 Yeah, and it did, yeah.
Hey Jim, this is Jason.
Yeah.
I ran. You and I talked last week, right? And I ran. I'm assuming the same example, and I got the little branching. Well, the terminal thing that I got was basically log ln infinity and t max leading to m, which leads to log k in one of those arrow plots.
Yeah.
Was that the final kind of thing to kind of
Yeah.
pull from that vignette? Yeah. So my question is, like, if you were to get what your prediction of m from k and l infinity, how do you then get that from this?
Yeah, so one way to walk through this is to so Jason, I'll share my screen and I'll get to that question in a second. Jason was basically like, how do you access the predictions and like how do you summarize the output, which of course is a good question. So so if I run it here, let's see. So I did in fact run it, I think. I'm trying to figure out what I actually ran it through. Oh yeah, no, I was still running the polymerase and poly example. So I'll just switch over to the vignette and run it locally and then really kind of back up to your question here, Jason. So I'm sorry, I'm trying to zoom in. Can people see my screen okay online and in person? Okay.
Yeah, let's.
Great. So, all of these like kind of start the same way, which is in this case, loading the fish tree complete, which I'll get going because I got a new R session and it might take a little while. And then in this case, I loaded this. There's an Excel file that Fen has on the website that goes with their 2015 paper, and I made a local copy of it because CRAN being CRAN has a very specific way of loading data, and I reference them in the reference docs for that, and point at their URL, and hopefully they're okay with that copy that I've made. And then let's see, again, I convert it to this genus species with an underscore. I dropped duplicates, like stocks within species. There were a couple duplicates in the Thanadol database, and I didn't want to complicate this example with that stock within species stuff. And then here I'm just gonna look at the data, and the data is basically complete is the thing. So if you do the summary of the data, wait, no, there's a couple NAs here. Okay, so there's 12 NAs in log L infinity, and 3 NAs in log T max, and 12 NAs in log K. And so I drop some of the species. Again, I use this keep tip function to drop the tree just to this set of species I care about. And the trimmed phylogeny for the Thanadol database looks like this. And then I drop species that are in the Then database that don't match immediately in Ravoski I drop, which leaves me with 210 records instead of 230 or something, so it's like, again, like 10% lost coverage because of the kind of lack of a worms ID to easily link the two. And then let's see, and so in this trimmed version of the data, I've still got 12 NAs, 3, 12, so I've got some NAs in here. And then I'm going to fit the model using this structure where K goes into Tmax, L infinity goes into Tmax, and Tmax goes to M. And so that structure is not a regression structure. It has, we can see the graph in a little bit, but it's basically saying that M is conditionally independent of K and L infinity, conditional on the value of longevity log Tmax. So that conditional independent structure is saying, first of all, if you put all three into the same regression, they're not independent because K and L infinity are correlated with each other, and they're also correlated with longevity. So you don't want to put all three into it. In regression land, we'd call them collinear, and and you just arbitrarily kick one of them out based on a variance inflation factor. But that's regression training is sort of the opposite of what you actually want as an ecologist, because they're collinear because they are ecologically related. And so, my spiel is basically that regression modeling is a lie and has tricked us into this way of thinking that's the exact opposite of how you actually want to think as an ecologist. And, in this case, I'm setting up a causal structure that I chose kind of for this benefit of having M be conditionally independent of growth given longevity, so that if you have a longevity measure for a species, it'll ignore anything about growth parameters. But if you're missing longevity, then it'll kind of revert to the growth parameters for informing your model. So I can do this grid search model selection, and it'll run it on 8 models. And then I can, get AIC for each of them and select the one that. So by AIC, I'm doing this grid search on an OU, Ornstein-Uhlenbeck, like a mean reverting random walk instead of a Brownian motion. Lambda is estimating additional variance at the tips relative to the ancestors. And so it's sort of like a measure. There's papers in PCM that are basically saying that's a statistical measure of whether your phylogeny does anything or not. So as lambda goes to 1, phylogeny is explaining all of the pattern. And as lambda goes to 0, it's ignoring phylogeny and just saying every tip is independent. And so it's essentially a model-based way of saying, is phylogeny useful in explaining your patterns or not? And then kappa is this nonlinear transformation of the branch lengths that Sabrina brought up. So like you might have some outgroup, like in this case, if you plot the tree again, you know, most of them, I wish I could remember the function to add the tree, the axis label, but somebody could look it up in ape. There's a few taxa that are way more unrelated than these other ones. So like rockfishes are here, I remember, and all the rockfishes diverged from each other in like about 20 million years ago. You know, some of these are going back 300 million years or something, you know, to the time of dinosaur. And so, you know, maybe rockfishes are more different. You know, maybe it's these ones are more similar to fishes than you would think just based on data alone. And so the kappa is basically transforming the branch lengths by an exponent. And so a kappa less than 1 makes these branches longer and these branches shorter than you'd otherwise think. And so it's basically rescaling really close relatives and really distant relatives. And so if you do model selection, you get that the best AIC model has both the lambda transformation and the kappa. And if you then extract that and look at the parameter estimates, oh wait, no, that's not in the summary table. So I'll just have to do psin best opt, just look at the optimized slot. So the logit lambda is 2.2. So I can do p logis of that value. So lambda is about 0.9, which means that evolution is explaining 90% of the differences among species. So there's a lot of phylogenetic signal. And then log kappa is negative 2.7. So kappa is 7.6. So there's some evidence that species that are closely related are more different than you'd expect otherwise, and species that are really hugely different are more similar than you'd otherwise expect. Just if it was like a random walk evolution process. So anyway, so then I can visualize the output so all of, you know, Jason, getting back to Jason's question, let's see, is all in this as Philo4D. So Ben Bolker has a package called Philobase. That is basically like a set of data structures for trees that have traits on them. Okay, so apparently Francois Michonneau succeeded Ben Bolker as maintainer of the package at some point. But you know, I'm not plugged in with him that particular, you know, but and they have an object called a Philo4D object that I convert the output to. So my Philo4D, and this is just, I mean, somebody could look up the let's see, my 4D, it's a Philo4D object, attributes, I mean, I think it's an S3 object, so, or no, I may be on. So anyway, here, I should do the names. Long story short, my memory of how to interact, one way to interact with it is to just query the data. And so this is the data frame of imputed traits for both all tips of the tree and all of the ancestral nodes. So let's see, I don't remember offhand what the best way to query that is. I have code that I use that I just copy paste that I haven't memorized, where I pull out, like if you have a species in the tree, like one of those clupeids, you obviously will want a function that looks up what row of this data corresponds to that tip. And I just don't remember offhand how to do that using the Philo4D package. But the point is, it's a mainline package, and you could look up code to do that. And as package maintainer, I'm not, you know, kind of outsourcing that kind of set of, you know, like in fish life, that used to be there. I used to maintain like a function. Well, I still maintain fish life,
And so there's a function called search species that does that sort of lookup task for you. The other thing, yeah?
Just really quickly, the object that I created, it does have a label column which had the species names, obviously making that job a lot easier. Yours, yeah.
Oh no, here we go. I was just pulling out the data slot of it. No, so yeah, Jason's right that it has, obviously that class of Philo4D has a print S3 generic. So when you type in the name of it, it calls the print function on it. And that print function appends it, with a label and the node and the ancestor, the edge length, whether it's a tip or an internal or the root. And so, if you're interested in Gambusia holbrooki, seems like that should be whatever. That here's the value, and I'm just gonna to kind of be pedagogical, I guess. I'll we can go into data, and let's say Sardanops sagax, which is the first one that I recognize. Let's say it doesn't have longevity information. If I put that as an NA and rerun the model, just to confirm, I'm putting in an extra NA value for longevity for, I think that's is that sardine or herring? Does anybody know? Sardine. And then I run the model again. I'll just kind of do the brute force grid search again, just because I don't want to mess with code. And then I converted that Philo4D, it'll have an imputed value for that NA, because it's doing it's doing the mixed effects model in the background at the same time as it's fitting parameters. I think that my as Philo4D function allows you to extract, instead of the estimates, extract the standard error. So an obvious question is like, okay, you've got a imputed trait value, like for, one, Yaneli asked me at the beginning, like, what did I do? We presented this at the Alaska Center, the North Pacific Fisheries Management Council plan team, groundfish plan team, as an estimator for M for Pacific cod. And Pacific cod M is fixed a priori and has this huge leverage on the ABC. And so, one way that you could run this, maybe what I should do actually in a second, is I could just add to that data frame a final row named Gaddis macrocephalus. It's a bunch of NAs, and then run the same model, and it would give me the imputed values for cod. What I actually presented to the plan team was not all NAs. It was a non-NA value for the longevity that Steve Barbeau gave me based on the average of the top 5 specimen records in the fishery in the survey, which was like 14 years, appended to the Thenodol database, and I used that prediction, the resulting prediction from that appended row, as the mean of as the mode of the prior. So that was my answer to you, Yaneli. Was that you want to follow up on that cod thing, or should we just kind of continue this example for a second of that NA for sardine?
I think this is good. Keep going.
Okay. Yeah. So I mean, so again, okay. Well, annoyingly, Philo4D is reordered this based on the tree order. So Sardanops sagax is buried in here somewhere.
I saw it within like you missed 10 or so.
Okay. I don't, again, like I'm not 14. I'm not like brilliant at the PCM universe constellation of R functions, but yeah, so it's 14, and then let's see, I'll Yeah, so I'm just gonna do that again so we can have it all on the same terminal without line wrapping. So this, this is the, maybe I'll do a screen snip because I want to compare that with the data. I mean, I just want to, so there's that, and then head data. So yeah, so I didn't change the family, and so the model by default is doing the same thing as Philo LM, where it assumes that there's no measurement error. So it's assuming that in this case there'd be no way to estimate measurement error because there's no replication of measurements within species. I mean, actually, that's not true. I guess I could estimate measurement error. I don't know what would happen. We could try it in a second, but the point is that by default, it's assuming that all of the values are measured without error. And so if there's a value there, it's going to, the estimated latent variable will be identical to that value. And that's what we see here, where the inputted log m is negative 0.84 and negative 3.6 and 5.12, but then that NA has been converted to 1.92, which is the value of longevity that's most consistent, both evolutionarily and within the trait covariance. So like in some sense, this is Kriging, like taking the spatial model example, this is sort of like a Kriging where it's assuming that all of your measured values are known exactly, and it's just doing this sort of Gaussian process to fill in missing values. So I think that was a really long way of trying to answer a question Jason had about like, how do you, or was that your question, Jason? I took your question as like, how do you get the output for a given species?
Yeah, well, yeah, no, this is getting there, right? Because the question would be if you wanted a natural mortality measure that you didn't have for a species, how could you leverage this database and this way of using phylogenetics and this tool and so forth to get it? And if I'm hearing you right, it sounds like you append basically the inputted values that you want to predict it from. So in the case of I want to predict from L infinity and K, and maybe even T max or whatever it is, I would add a species to this database, but leave the M and NA and add the other ones, add L infinity and K and T max, and then run this script and then just pull out, like you said, the Krieg version of what the M would be. Is that one way to do this?
Yeah, and that's, so yeah, Jason's like, hey, if you have a new species, how do you predict it? I was thinking again, I mean, like generally people want a predict function S3 class, and like if people are using this a lot, I'd be happy to do that. And TMB has like a new thing since I built VAST where you can like it's dynamically remapping, and so you can, without recompiling the object, the TMB object, you can plug in data to make predictions faster than it used to be possible. And so I could make and basically ape, the interface for this would be this add.tip function that ape has. So, Jason, you could just, in your session, you could type add.tip to see if you want that instead. And that would allow you to make a prediction without refitting the model. But that would sort of increase the code entropy, and be like an extra thing to maintain. And so the easiest way to do it is just ask people to add a new row to the database. So in this case, I'm just gonna try this. Gaddis. Does anybody know is macrocephalus? So this, I mean, this will be a miracle if this works, but data equals rbind data new row. Names new row
equals call names data. You know, of course, like this is where I'm annoyed with R. Let's see.
I think you have a bunch more columns. Isn't that the problem?
Oh, is data like a bunch of stuff?
It's a bunch of crap now. Yeah, I thought so.
Well,
Maybe not.
I thought I trimmed it.
Oh, okay. Sorry.
No, don't apologize. Call names. Oh, it's call names date. Yeah, okay, so it's call names. So like it allowed me to like R allowed me to like put a slot on something that didn't make any sense. Call names. Okay, so now new row is a mate. I'm just gonna start over. Yeah, new row. Okay, so new row, and then I'll put call names on new row, and then I'll try to add it. Yeah, and then let's just check the tail of this. Row names, data, reverse that. I don't know if this will work. Doing an assignment on reverse. Gaddis. But yeah, again, the point is to have software where like your real challenge is just dealing with R again, Calco, Grammus. Oh yeah, Gaddis. Oh yeah, okay, macrocephalus. I just always end up thinking about Pollock. Macrocephalus. Yeah, okay, it doesn't. Hold on, we'll get this. Okay, one. I'm sorry, Jason. This is probably like convincing you that this is not very user friendly, but it's all.
No, we're right there, right? I mean, like literally, you're just trying to get a name on something. No, this is making intuitive sense. And it's kind of you're drawing out the
drawing out
excitement.
Yeah, exactly. Yeah. Thank you. That's a nice way to put it. For those in the room, Jason made a funny. Miko, it would be amazing if there's a way to set up the speaker system in here for whatever room, just so if I do this again, I feel less uncomfortable translating, but. New row. Okay, so I think this will work. Data, so tail, data, R bind, data, new row. Okay, so now we've got data with an extra row, and then we'll just see if, I mean, I think that if we didn't spell it wrong, I'm sure the Roboski tree, fuck.
Does it, you're putting in zeros instead of NAs, is that all right?
Oh, yeah, you're so right, Jason. Okay, so data 211 is NA. I just wanted to, Jason pointed out that I was putting in zeros. I was putting in actual data, which would just mess up the model instead of putting in NAs where I'm telling it to impute those values. And then I'm just going to assume that it's in the Roboski tree. It should throw an error if it's not. So, okay, check that all data labels are present in the node labels of the Roboski tree. Oh yeah, that's because I already reduced the Roboski tree down to the same set. So I'm going to reload the full Roboski tree, and tip tree. Oh yeah, and then in this, so that's the full tree, and then I'm gonna reduce it down. Species to use, I'll just say, is the row names of data, and then we'll see if this works. Keep. So n tip of the tree has 210 trips, which is right. And then the tree has, I mean, okay, so this is useless, but there should be Gaddis calcogram. There should be Gaddis macrocephalus in there somewhere. And then I'll try running this full grid search. I mean, again, so yeah, so it's running. So
you know, eight models later, PSEM
If this,
best.
if this does work, would you consider this little chunk of an example, adding it to the vignette?
Yeah, and Jason's asking if this works, adding it to the vignette, and yeah, I can do that. That makes sense. That makes sense. Yeah, and then my Philo 4D. So I'm just 4D, and then with any luck in here somewhere is, and again, there's got to be some better utility than just scanning by eye, because I don't think can you control F in term? I don't think you can control F in terminal output. Wait, can you? Are you using RStudio or something? Yeah, this doesn't. Yeah, okay. Is that a Mac? No. Yeah, I could grep on that, but the problem is it's like a printed output. Like I'm scared how this is like, I mean, PCM is like, I mean, like the point is to get on software where other people do it, and like compared with fisheries where nobody does this, there's a bunch of packages doing PCM. Like here, I'll just, again, be kind of didactic. Comparative methods, CRAN view, CRAN task view, phylogenetics. So core packages 8 phylobase. So those, those are what we're using. Geiger, PhyTools. PhyTools is where that add tip function is that I mentioned that I could fold in. And then tree visualization. So like, Philo signal would be up here, except it got booted from CRAN. Yeah, archived. I mean, I put an issue in for Philo signal on GitHub, and they're going to get it back up because it depends on 80 Philo, which got booted too. So there's like this like Bates domino effect. But anyway, the dream is to get fish, tree search, for instance, like, or I don't know, maybe that's the wrong thing. I don't know, but there's got to be some function in here that does what we want, where you grep. Until then, I'll just keep brute forcing this to try to get to the end of our example. Okay, Gaddis macrocephalus. So it was a bunch of NAs, and here's the predicted Thanadol equivalent predictors of those growth and M parameters. And wait, was I showing Gaddis marhua? No, Gaddis microcephalus. Yeah, and I think that the log M is 0.98. So so it's the Thanadol with no information is saying that cod should have an M of 0.37. I think that the mode of the predictive distribution that I gave to Steve Barbeau was slightly different because we used a longevity of 14. I mean, we could actually run that too. Data 211. We're kind of running out of time, but so I'll just put in for the third column, which is log Tmax, I'll put in log of 14, which is the value.
Jim, I mean, the point here is we could put in our L infinities, our K, and our T maxes, not leave them all blank, just the M, and allow those numbers to interact, right?
Exactly. And so yeah, Jason's asking, like, how would you use this in practice? Yeah, my claim is if you want to predict M, you could, and I have this in the paper, like if, the better, you explain 80% of the variance if you have longevity. So if you have longevity information, that's a better estimator. And you could use this by putting in your longevity information in that column and predict M. But let's say you've got something like Greenland shark where we don't we can't age it because it doesn't, or dogfish or something because they don't have bones and we haven't spent the money on a lens study. And so in that case, the best information is some mix of growth parameters and longevity information based on studies of related sharks, hypothetically, you know. And so in that case, instead of putting in the longevity value, which you don't trust, I'm sure there's a longevity published for any of these fish, but you don't trust it. And so instead you could put in the growth parameters. I don't know. Well, anyway, that's a bad example because I don't know how you'd get growth parameters without aging, but
Hey, Jim,
yeah.
this is Lewis. I have a question about, besides the point estimates for these trade imputations, can you get some type of precision, or how do you know if one estimate is better than another aside from the evaluating the entire phylogenetic model?
Yeah. It looks like I didn't. Let's see. That's a bummer. I definitely had at one point, maybe it's on the dev branch or maybe I lost it when I did a merge, but I had a way of getting the standard errors from the TMB object into that Philo 4D. Like medium, you know, long term, it'd be nice for somebody to connect, you know, me or somebody to connect with the Philo-base people to get their Philo-base object. Lewis was asking about how to get the standard errors, sorry. It'd be nice to work with them so that they have a data structure like an S3 class that has the point estimates and the standard errors, you know, and that would be the best and longest route, you know, and then I could use their data structure. In the short term, I can just add an argument to this as Philo 4D object that loads in the standard errors, which I thought I'd done, but
Gotcha.
maybe I did that. And then, you know, the immediate option is just, you know, knowing, you know, so it's the PSEM is an S3 class, or I think in this case, I loaded it as PSEM best, which has a print statement, but has a bunch of stuff on the background that's, so, you know, opt SD as list, what, or let's see. Yeah, anyway, you can, you know,
Yeah,
somebody.
the SD report is in there. It's in the object.
Exactly. Yeah, exactly.
Okay,
So, you know, within, you know, 10 minutes of kind of syntax errors, you know, we could recall the syntax to pull out the standard errors using the SD report output of the TMB object. But it would be nice to have a more intro user path to get that same, you know, like an S3 class.
yeah, because they're not going to be able to map even the stuff that's in the SD report onto those specific predictions very easily.
Yeah, exactly. So I'm trying to remember. I mean, I literally did this for the plan team, and so I could look at my code there. I mean, you know,
That's fine. You don't have to go through it now. I was just wanting to
no.
learn how we get that.
Yeah. The short answer is like, yes, it's possible to do. The longer answer is like, I don't remember the syntax I was using when I did that last. So here's the script I ran for the Alaska Center, and it just does a loop through different models and a loop through different species added to the tree, and then it looks like I'm pulling, yeah, exactly. So as Philo 4D, I used to have a what statement in there that I obviously lost when I did a merge cleanup. So I'll just add that back in and have that in the next release again.
Awesome, thanks.
Yeah. Just selfishly, I mean, well, I mean, maybe the bottom line is like we should switch to discussion, but like there's a bunch of fun research topics that I'd love to do. I mean, Sabrina and I have been talking about reproductive traits for rockfishes. I don't know if anybody is tickled enough that they're interested in emailing me or brainstorming right now, but like presumably there's sort of a bunch of side projects that people could, you know, do without me or talking with me or whatever, you know, so. Yeah. Yeah.
This is really cool. So if I think of a practical application of a method like this, one thing that comes to mind to me as somebody that builds ecosystem models where you have a bunch of species with a bunch of parameters that you have to find values for, is to use a method like such to kind of populate as many as you can
Totally.
parameters. And I think that as I was building the Atlantis model for the Gulf, I think I used some of your fish life
Totally.
as well,
Yeah.
which is really cool. But inevitably, you do that, and then like when you bounce ideas around with people, like they'll come to you and say, well, yes, but since you use this for the Gulf of Alaska specifically, you should have gone and taken those parameters for biometrics and all that from the stock assessment instead,
Yeah.
or from some very specific data source that is pertinent to the area. So
Yeah.
I kind of was wondering how you typically deal with that, kind of like the power of and the brute force of something like this
Yeah.
versus like the fine-grained approach.
Yeah.
People are kind of on your tail about that.
Yeah, so it's Alberto, right?
Yeah.
Yeah. So Alberto was asking, commenting that like, yeah, fish life and other databases can be useful to fill in missing values for ecosystem models, but like you inevitably get local people that are like, well, that, some of that stuff is from Fishbase and shit, and you should have done it by filling in known values, and you should have like a regional customized version of this that we trust. That's what I hear you saying. And yeah, I mean, that's 100% the goal of having Phylosem, is to branch off like the simple to use software. It covers 90% of the fish life. Like, it doesn't have the multinomial distribution that I put in fish life. And it definitely doesn't have the like stock recruit stuff that I put in fish life, but or the generation time or whatever, but it covers a lot of the use cases. And so my feeling is that each region worldwide should have some regional expert on phylogenetic comparative methods who has assembled or knows the sort of best database, and then like you coming into the Gulf of Alaska should be able to go to that person and get like, hey, here's the version that we trust of the database, and then you just make small modifications as needed, maybe adding columns or something, and then run that through Phylosem or chosen PCM software. I mean, yeah. So, and I mean, I think like ICES, like for instance, like Martin Lindegren and Mark Payne have their work where they've compiled life history traits, and then they line that up. They have a project called Be Helpful, I think. That's like one of those Europe ones, big multi-million Europe ones, where they're assembling a database that I think Bastien Marigot is involved with. So like academics do this in ICES, but like really the US science centers have just never had like a regional version of this PCM stuff. And my claim is that we should. So like another example is like a lot of our bioenergetic models are fundamentally based on some energy density values for mass balance, and those values are just like on a spreadsheet that people pass around, and I don't know what they do with it. And like I think Greenland turbot just takes the values for air-tooth flounder. There's like a lot of reasonable kind of guesswork that is put into that spreadsheet, and it'd be nice to have like more of like a data science strategy for that stuff, where you publish on GitHub or something what's the database of your bioenergetic values, and then people that come in can use that and make targeted modifications, and you reuse it. Was that? Yeah, Sabrina.
Along Albie's line, so if you're looking at PCs, or maybe you provided stuff for that, but considering that, so just one value for that species. So considering that a lot of traits are plastic, broadly distributed throughout Alaska and the California current, the values are going to be very different.
Yeah.
So what do you think is like, so I can start somewhere, it's a great place to start. Traits, but thinking about us as the traits are gonna change. So is there like habitat variables that you can build into this that would kind of
Yeah.
help that out? Or
Yeah, there's so many interesting.
on the tips or
Yeah. Yeah. So
future?
Sabrina's asking about like that. Yeah, like individual within stock within species, and like how that's driven by habitat, and basically my like 10-year goal would be to merge, something like this and VAST and GLIM-TMB. So they're basically all different GP models. Like any mixed model is a GMRF, and so you could, like, what would be nice is having a function where you could put in a phyllo class and a time series class and a mesh from INLA, and you'd get like the phyllo by space by time that you could specify. And computationally, it's not really that hard. It's just kind of a data science thing to get people familiar. So like, I hate the formula interface because I think regression modeling doesn't work for making predictions of counterfactuals. And, so like, this is my first tipping the toe dip of like a package that's as simple to use as LM, I think, but using the SEM interface instead of the formula. I've got a time series package called DSEM that I'll publish next year, hopefully, that does the time series extension. And then I'm hoping to work on TinyVast, which would be the sort of like SEM for spatiotemporal models. But at some point somebody needs to talk with Ben Bolker and Molly and other, Sean, and like make the software that does this, but also allows you to put in a phyllo object, or like, and it gets into CS land that I'm, computer science stuff that I'm not qualified to do, but I could write the model. I just can't make it user friendly for other people to run. Well, okay, so we're at time. My car's either been towed or not. And yeah, thank you everyone for coming and online.
Thanks, Jim.
Thank y'all.
Is what is new.
And I'm gonna go to Agua Verde to get a quick snack in case anybody here wants to walk over with me.